A very good evening to all the attendees today, and thank you all for joining this eminent foreign lecture series. So today I'm sharing screen with Professor Dr. Vishwa Chatterjee, Vice Chancellor of University of Engineering and Management, Jaipur, and Professor Dr. Aniruddha Mukherjee, Dean Academics, UEM Jaipur. And along with us on screen, we have few students from electrical as well as mechanical engineering. And above all, today we have the guest and the keynote speaker, Mr. Paul Martin. So I welcome you, Mr. Martin, on behalf of the entire IEM UEM group, and wish that today we are going to have a very energetic and enthusiastic learning session for all the attendees. So before we start the session, I'll just take a minute to introduce Mr. Martin. Mr. Paul Martin has bachelor's and master's degree in chemical engineering from University of Waterloo, Ontario, Canada. He spent his first 5 years in water treatment and environmental remediation industry, developing new process technology. And for 25 years, he has worked with Zeton, the world's premier designer and builder of pilot plants for chemical process industry. He has designed and built laboratory scale, pilot, demonstration, small works and small commercial plants for bewildering variety of chemical processes, including involvement in projects which have led to commercial facilities worth many millions of dollars. He has project experience in monomers, polymers, biomass conversion, hydrogen and syngas production, and electrochemical processes. So Mr. Martin also is also an active advocate for transition to renewable and non-emitting energy sources to address the risk of global warming. So as a project of lifetime, he has worked on the conversion of gasoline car to full electric drive. I would say that this was his dream project, and along with his son, he took up this project and completed successfully. So about the topic, I'd like to brief that the talk will not be very much focused on technical part, but exactly the motivation behind converting a vehicle to electric drive and the working efficiency importance of electric vehicles in future. So that was a brief about Mr. Martin as well as the topic for today. So from here, I'll hand it over to you, sir. You can please take it over.
Thank you very much. Welcome and good evening to everyone. This talk is about a passion project of mine. As mentioned, it's not really related to what I do for a living, but the project led to all sorts of work later on and informed all sorts of work that I was doing in my professional career also. So as they say, no education is a waste, and this project was definitely an education for me and also for my son. So, okay, so now why is it not advancing? I'm having a bit of a problem advancing the slides. Oh, here we are. Yes, so of course, there we go. So as we're probably all aware, there really are only two sources of energy that we humans can access. One of them is energy from the sun, either today or from a historical sun. And the other is from the energy of the earth, whether that be the materials of the earth like uranium or the primordial heat of the earth, such as what we harness with geothermal energy. And the good news is we have this giant fusion reactor in the sky at a nice safe distance of 93 million miles away. So we can take advantage of it, or we can take advantage of the energy that it put up for us or nature stored for us over the long period of time. But this is really the ultimate source of all the energy that we use. And as we know, we can't really we can't really pull energy from nothing. We can convert one form of energy to another, but every time we do a conversion, we lose something. And so the laws of thermodynamics determine the transitions that we're permitted to do. And as I've said here, the first law is that there's only one game in town, and you have to play it. There's no other game to play. And the first law says that you can't win. And the second law says that if you can only really break even on a very cold day. And the third law, of course, says that there's an absolute zero, so it never really gets that cold. So these laws are so fundamental and universal that, and what's fascinating about them is that they were discovered before we understood why they were true. So that frames all of our dealings with energy. We have to deal with energy in the context of the laws of thermodynamics. Originally, we people had access only to the energy of our bodies, And as machines, we're about 15% efficient at converting food energy into mechanical work. We can be more efficient or less efficient, but it depends on the definition. But for the largest part of our history, we only really had access to about 100 watts of mechanical work for 8 hours a day from each person. And that's it. That's all we had. But eventually we got smarter, and we learned to exploit animals. And each animal is about 7.5 people. And so one person could now take on the power of, say, 4 horses and use them for the purpose of doing whatever needed to be done, moving things or digging or plowing fields or whatever was needed. And so that was a huge improvement for us. And of course, as we learned to exploit animals and the power of animals, we enjoyed that a lot, and we used it and used it more. And the animals are around the same efficiency as humans, on the order of about 20% efficient. But the problem with horses or animals in general, again, the problem was mass consumption. So if we look at the city like New York City in the 1800s, late 1800s, early 1900s, there were 175,000 horses in that city, with 2 million kilograms of manure per year. And they were piling it high, several stories high, and shoving it into the harbor. And the problems of horses in major cities were monstrous. And there was also a lot of people killed. They were quite dangerous. Their energy sometimes was not harnessed in the right way. And of course, horses also die. And when the horse dies and lays in the street, removing it is really a challenge. So the trouble here, horses make perfect sense in an agricultural environment where you can grow their food and the manure fertilizes the land. But when you try to put them in big cities, massive consumption equals massive problems. So in the early 1700s, we started to effectively convert heat into work by means of heat engines. And if you look at Newcomen's original engine, it was less than 1% efficient. But despite being only 0.7% efficient, what it did, it was just miraculous in that it removed the limitation of sustainability from our consumption of energy. Because in past, we were totally tied to either the sun or energy from plants that were derived from the sun. So we had to balance the desire to be warm in our homes against how fast trees could grow. And so that limitation of sustainability was a big issue for us. And once we could mine coal, and in fact we could use the steam engines to pump the water out of the mine so we could mine even more coal, we had a recursive technology for the exploitation of energy in, unfortunately, an unsustainable way. And when you think about a heat engine, of course, the way I like to think about it is like a waterfall that we put a water wheel in, and the height of the waterfall, or the distance between the top and the bottom, the distance in temperature between the hot reservoir and the cold reservoir, determines to some degree the efficiency that we can achieve through Carnot's equation. So but of course, that limit is a limit, and there's a limit based on materials of construction and so on. So you can only go so far. And this is an amazing graph. A retired professor in Alberta put this graph together, and I kind of updated it. And this is the progress of heat engine efficiency versus time. And of course, you see the dashed line up there is an arbitrary 77% per Carnot, and we're already getting to 60% with combined cycle power plants. And even with large engines like ship engines, we can get to above 50%. It's really incredible. Another thing to notice here in this graph is the giant jump between Smeaton's engine and Watt's engine. This is a logarithmic plot. So you can see why, even though Watt did not invent the steam engine, you can see why many people kind of concluded that he did, because he made it so efficient, so much more efficient than what was there before by such a large measure in such a short period of time. If we look at the gasoline engine, the gasoline engine is kind of the definition of the willingness of people to trade the efficiency for effectiveness. Okay, the gasoline engine is not very efficient. We've managed over the years to make it more efficient, but it still really is not very efficient. If we start with 100 joules and we feed it to a typical internal combustion engine of the size used in a car, not in a ship, we're lucky to get 20.5% out the back end. We lose about 18% or thereabouts just making the fuel, making the gasoline. And then the balance is lost by the engine as heat. And so it's rare that we tolerate processes that are so inefficient. But the reason we tolerate it in this case is that its efficiency is poor, but its effectiveness is really great. You know, it's a liquid fuel, it's easy to transport, it's easy to store, it's easy to transfer quickly into the tank so that you can refuel quickly. So it's the triumph of effectiveness over efficiency. And if we look at the various uses of energy in a vehicle, you can see the engine is by and away the largest waster of energy. In this instance, per this figure, 77% is lost as heat by the engine. But of course, the car, just like the horse, was a miracle. And I like to tell this story in the context of my father. My father was born in 1915, and he passed away in 2015 at 100 years and 1 month old. And you can imagine how different the world was between when he was born and when he died. But when he was a young fellow, they were still plowing the fields on the farm with horses. And when he saw his first gasoline engine tractor, he was just completely amazed by this thing, because you know, when it broke, you could fix it. You didn't have to shoot it. With a horse, if it steps in the groundhog hole and breaks its leg, there's no healing it. It's the best you can do is maybe use it as food. Or send it to the glue factory, but the utility is gone, and they were also very difficult. They didn't like to go where you pointed them. If there were two horses walking together and one had to walk in the soft part of the field that had already been plowed, and one got to walk on the hard part of the field that hadn't been plowed yet, that was easier. And so both horses wanted to walk on the hard part, and they kept pulling and pulling. You had to keep pulling them back. So this car, this tractor, which went where you pointed it, it was like a miracle. So my father decided, this is the future. I'm going to become a mechanic. And a lot of people concluded the same thing. And of course, the mass exploitation of cars became the problem. Well, here we are. At the same time, around the time my father was born, electric cars were as popular as gasoline cars. And in fact, they were the fastest thing on the road too for some time. As you can see, this Belgian fellow with his car that he called the Never Satisfied, La Jamais Content, went as fast as 66 miles per hour at the turn of the last century. And the peak sales were about 200,000 electric vehicles. But of course, the superior technology of gasoline won in the end, because battery technology was just not up to the job. When we look at the electric car, the amazing thing about it, though, is efficiency. So remember, we were talking about from energy source to wheels, or not to wheels, but to motor shaft. In the last example, we were talking about 20%. Well, this is now 75% almost. And even if we have to make the electricity from a fuel by a combined cycle power plant, it's still 42%. So we're talking about a gigantic gain in efficiency. And the nice thing about gains in efficiency is they mean reductions in cost ultimately, but they also mean reductions in environmental impact. And that's the real benefit of electric cars. Now, the big competitor in recent years has been hydrogen. And as a chemical engineer, I have a long relationship with hydrogen. Hydrogen is an old friend to me. I've been making and using hydrogen for 30 years. And the problem with hydrogen is that it's hydrogen. And unfortunately, hydrogen's properties as a molecule and its thermodynamics limit how effectively it can be used as a fuel, whether that be for heating or for transport. And in this instance, when we look at the fuel cell car, we have too many steps. We have a transmission loss, just like we do with electricity, and then we have the efficiency of making hydrogen from water using electrolysis of about 60%, and then compression of about 90% efficiency, and then the fuel cell, again, best case, 60% efficiency. Real ones that you can afford are closer to 50. And then we feed it to the same motor and inverter that we fed from the battery before, and we end up with 27%. So the efficiency of hydrogen is a problem. And of course, many people say, oh, it doesn't matter because in the future we will make electricity from wind and solar so cheaply that it doesn't matter if we make it efficiently. The trouble is, of course, that efficiency goes to cost. And all of these steps, they all have capital associated with them, which makes them costly. So the trouble with the electric car that's fueled by hydrogen instead of by recharging a battery is its poor efficiency leads to high cost. So why did the electric car fail back in the 1910s and 20s? Well, originally, when there were only 20 good miles of road in the whole community, it didn't matter to have a range longer than 20 miles. It made no difference. But of course, once they started building roads and better roads and making them longer, range started to matter. And the great thing about gasoline is its energy density per unit mass and volume is exceptionally high, despite the poor efficiency of the engine. And it's also very effective, as mentioned. You can distribute it very easily. So in North America, what happened is that every little corner store in the countryside became a gasoline station overnight. And all of a sudden, everyone wanted a car, and Henry Ford mass production ensured that they could afford one if they wanted it. And all of a sudden, the final blow, actually, electricity, in a sense, had a hand in killing the electric car, because the original cars were started with a crank. And of course, if you did cranking wrong, you would break either your thumb or your wrist when the car either backfired or started and you didn't disengage the crank quickly enough, you would end up getting injured. And so a lot of people, kind of fancy people, and especially women at the time, were not comfortable with an engine car. But then the electric starter in 1911 meant that you could just push a button and the car would start, and the rest is history, as they say. So why do we need the electric car now? What's changed? Well, the big thing that's changed, the huge invention that happened that made the electric car now make some sense, is the invention of the lithium-ion battery. And it's really two things. One of them is the lithium-ion battery technology itself, and the other is the fact that we have these little devices, cell phones and laptops and so on, mobile devices, and they're so valuable to us that we were willing to pay $3,000 per kilowatt hour for the initial batteries when lithium-ion was invented. And that consumption of very high cost batteries initially allowed the production of those batteries to increase, and they provided what's called a path to scale that ultimately gave the lithium-ion battery the possibility of becoming cheap enough that you could imagine using it in a car. But the real motivation here is climate change. We really need to deal with the emissions from burning fossil fuels. We didn't know about that officially until about the time that I graduated from university, about 30 years ago. But for the past 30 years, we've known and we've done nothing, or almost nothing. And the electric car gives us an opportunity to do something without paying too much of a cost for doing so. The other issue, of course, is that in major cities, even though we've gotten better and better at pollution controls on engines, the emissions from burning things is killing people. It's shortening their lives. And the nice thing about an electric car is it has no local tailpipe. So there's no toxic emission coming from the vehicle as it's driving. And that's important because, of course, we're driving right next to people that are going about their business breathing. Of course, the other thing is that right now we're exploiting cars, but there's a huge fraction of the population of the world that has no access to that technology because it's too expensive and they would like it. And if we expand the role of cars in the world to the entire rest of the world, as one would expect that we ultimately should, the burden of the fossil fuel emissions and the toxic emissions would just be tremendous. So ultimately, to deal with all of these problems, we need to transition to renewable or non-emitting forms of energy, and the electric car's efficiency greatly helps with that. So here's the motivation right here. Here's a graph of the concentration of CO2 in the atmosphere, and it's not coincidence that starting in about 1800, when we started exploiting fossil fuels in earnest, that the CO2 concentration started going up. And we know this from measurement. This is not supposition. This is not models. This is reality. So we have to cope with it. And it's the way I've put it is that we had a great party for 300 years on the stored energy of the sun in the form of fossils, but the party's now over, and we have to sober up and clean ourselves up and stop mourning, stop denying it or bargaining with the problem, and get on with solving it. And electric cars are definitely part of that problem. Of course, I'm very fortunate. I live in Canada, and 80% of Canadians have access to a grid like mine or better. So my grid is only 40 grams of CO2 per kilowatt hour because it's mostly nuclear and hydro with a little bit of wind. And what remains is natural gas at a fairly small percentage, I think year-round average of about 7%, and no coal. We burned our last coal in 2013. So in Canada, we have a beautiful grid. And of course, that makes electric vehicles, when you have such a grid like this, which is the envy of the world, electric vehicles really become kind of an obvious choice, you know, what we would call a no-brainer. Of course, that's not true everywhere in the world, and you can see the carbon intensity of electricity in the world is not uniform, and it's very high in some places, and so this is still the primary problem we have to work on. But even so, even in places where the intensity of the grid is not so good, where there's a lot of CO2 emissions per kilowatt hour, the benefit of the electric car is that it provides that elimination of the local toxic tailpipe, which we can't really scrub. We can't even really continuously monitor it. And the electric car just doesn't have that local tailpipe. So in net terms, even on a life cycle basis, electric vehicles provide benefit even in very dirty grids in the world. And of course, the grids in the world everywhere are going to get better and better as we implement more renewable energy. Now, if you want to move people, you want a low frontal area, you want to go slow and steady. And this picture is from a really wonderful resource that I encourage you, if you're interested at all in energy, and you should be, because of course, this is the big issue of our future, you should read this thing. I've given the web address to www.withouthotair.com. It's written by a fellow who's now passed away named David Mackay in the UK. And he does a very clever set of evaluations of looking at what the transition to renewable energy or non-emitting energy or sustainable energy will take. He calls it sustainable energy without the hot air. And it's a refreshing look. Although he does do one thing that I think is quite wrong, and that is that in order to make the analysis simple, he takes every bit of energy, whether it's heat or work, and he converts it all to joules, or in fact, it's kilowatt hours per person per day. And by so doing, it's almost like he's committed what I call the first sin of thermodynamics. He's sinned against thermodynamics because heat and work have the same units, but they're not worth the same. It's like comparing say American dollars and Jamaican dollars just because they're dollars. They're not worth the same. So of course in Canada there are people who have the notion that cars are just bad. You know, we should just get rid of cars, and they have a point. But of course the trouble is that they're often arguing that other people should take public transit. And the amazing thing is that here in Canada, because the grid is so good, my electric car can compete with a diesel bus that has 60 people on it. So that's the kind of improvement that we're talking about. We're talking about an improvement of 97% in emissions from source by just switching the type of vehicle that you drive. That's pretty impressive. So now we can talk about the fun part. So In 1988, when I was a young and foolish man in university, studying chemical engineering at the University of Waterloo, I bought a 1975 Triumph Spitfire. Now, this car was very pretty. It was beautiful. In fact, you can see the picture of the car in the upper right-hand corner. But it was very poor condition. That's why I could afford it as a student. And I took it home and I showed my father, who was a mechanic, as I mentioned, long retired by that point. And he looked at me and he shook his head and he said, British cars, they're not made very well. And he was absolutely right. This car had the tremendous advantage that you could lift up the hood or the bonnet, and the engine is just sitting there on the frame, accessible for working. And I thought, well, if I'm going to learn how to work on engines from my father, this is a good car to do it. Oh, little did I know that I would have to work so much on that engine, because it was such a piece of junk. You know, the cars in the 1970s, especially British ones, they were made in the lowest ebb of quality control, probably in the history of car making. And so this car was very pretty. It had a beautiful suspension. It was very reliable going around corners. It had a very underpowered engine and very unreliable engine, but it was very pretty with this Italian design. And so I was very attached to this car. And then I met a girl when I was working, and she didn't like that car, but I got married to her anyway. But I kept the car. And the trouble with this car was that even though I had taken the engine out and I had replaced it with a larger Toyota engine and a more reliable transmission in the early 1990s, it just didn't really fit. And I kind of lost interest in the project. And the car, being British, it was kind of almost soluble in water. So in storage, for a time, it had to sit outside underneath a tarp. It got very rotten. But I kept it, and my wife kept nagging me, "Oh, get rid of that piece of junk. I never liked it anyway." And I said, "No. I'm going to do something with that car one day." And then finally, when my son Jacob, you can see in the picture below, was 11 years old, we decided, okay, I'm going to make an electric car from this thing. Otherwise, it's junk, so why not? Let's do it. So here was the plan. I decided to buy lithium-ion batteries. At that time, the popular battery was a prismatic lithium iron phosphate battery. And I had enough money to buy 22 of them for the front and 10 in the back, which gave me about 18.5 kilowatt hours of storage. That would give me a range of, I hoped, about 100 kilometers or about 61 miles. And so that was the plan. And we went forward with this project, and that's what we'll be talking about here. So here are some details for some people that are really interested in the details. You see, when you remove the bonnet of this car, the fenders come with it, and you have perfect access. So it's the easiest car to work on. I used an induction motor, an AC induction motor, three-phase induction motor, specially wound for use in vehicles, made by a company in California. The properties of electric motors are really wonderful for car applications, because once you get above a very low speed, like above about 100 RPM, you have a flat torque curve all the way up to the maximum power. So that means that this car had 120 foot-pounds of torque at almost 0 RPM. The second you touch the accelerator, the car would basically launch forward. Just fantastic. So the possibility of performance was really excellent. And that was more torque than this car with the original engine could ever possibly generate. And yet you have it accessible to you at 0 RPM. That motor is controlled by an inverter, a three-phase inverter that, again, is used in vehicle applications of all sorts. It's made by a company called Curtis, and it can generate forward currents of as much as 650 DC amps, which is on the input side, which is really quite a lot of current. And the motor, is designed, it's paired to use with this inverter, and so the motor can handle it. So although the motor's nominal power rating is less than 20 kilowatts, the motor can do easily 50 or maybe even 65 kilowatts for short periods, which makes it a much greater performance than the original car had. And of course, being AC with the right inverter, you have the benefit that you can do regenerative braking. So instead of relying on friction brakes in order to slow the car down, what you can do is you can use the motor as an alternator and use the inverter to convert that three-phase AC back to DC to recharge the batteries. And that eliminates the brake wear almost entirely. Pretty much the only time you use the mechanical brakes on the car is to hold it at a stop, when you're stopped on a hill, for instance. And that regenerative braking gives you about a 15 or 20% improvement in range, which is also pretty incredible. You'll notice, if you can see in the picture, in the lower picture where I'm putting the motor in place, there's a red plate, and that plate bolts to the existing, the Toyota transmission that I had put in the car when my father and I converted it to the Toyota engine to get rid of the British Leyland garbage that was in there before. And that plate and the hub that mounts the flywheel and pressure plate and so on that had been previously associated with the engine was something that I was able to just buy. So it was kind of, as we say, pushing the easy button, spending money instead of doing the hard work of making a precisely aligned transition between the motor and the transmission. And if you do this poorly, this is the most important step. If you do this alignment job poorly, you'll end up with an unreliable arrangement. You'll end up burning out input shafts on the transmission. But having a transmission is really wonderful. It gives you options. So being a chemical engineer, of course, I was very interested in the batteries. And one of the things that I wanted to do in the project for the project to be considered successful was I wanted to ensure that I got good data out of the energy efficiency performance. So I made sure that I could accurately measure how much AC electricity went into the charger and how much DC came back out of the battery, so I could do accurate calculations. And the beauty of lithium-ion batteries is that they're extremely efficient. I mean, they're higher than 90% efficiency once all the ohmic and polarization losses are figured in. And the other great thing about them is that really the process is very gentle. It's just lithium ions moving from the anode to the cathode and back again. The volumetric changes in these materials between charge and discharge can be managed in such a way that they're not very great. And as a consequence of that, the battery can last a long time. At the time, my batteries were warranted for about 2,000 to 3,000 cycles before they lost 20% of their capacity. And some that I bought recently for a solar project up at my farm, they were rated for 4,000 cycles. So the cycle life of these lithium iron phosphate batteries is really quite exceptionally good. So when you look at what the batteries look like, they're layers of anode and cathode, and with a plastic separator between them, and then that space between them is filled up with an organic solvent that has lithium hexafluorophosphate dissolved in it, and the lithium moves between the anode and the cathode and back again between charge and discharge. Here's the torque curve I was mentioning. So the orange line here, I don't know if you can see my cursor, but if you can, the orange line here is the torque, and you can see that the torque starts out very high and continues very high all the way to peak power, the green curve being the current, and the current is related to the power because the battery voltage is pretty much constant with these things. It doesn't droop very much. So here's kind of the key slide from the point of view of the decarbonization guy, you know, from my perspective as somebody that's really interested in energy. I compared the gasoline engine Spitfire, original one, with its 1.5 liter Leyland engine, against both my Prius and against the car converted, which I called the E-Fire. And you can see that the energy used from source drops rather dramatically by virtue of that efficiency, and the CO2 emissions from source drop by 97%. I mean, that's just incredible. It's not zero, but it's pretty close. So imagine, and that's comparing it to this Prius. See, I own that car, and that's my real performance. And it's 94% better than my Prius, which is the best gasoline engine car that you can buy in Canada that doesn't also have a plug. So there's no comparison here. The performance is absolutely incredible. On a money perspective, without carbon taxes, it's still a little bit hard to justify, but that's why the government gives kind of some incentives if you buy new proper electric cars. Of course, they gave me nothing because this conversion process is not something that they really care about or approve of. They're really interested in people buying cars from Nissan and Tesla and companies like that are making them. So here we go. Here are some pictures of the progress of the job while we were doing this. This is in my garage at home, and you can see it's not very neat and tidy, but that's okay because we are all about results here. So here I'm pulling the engine. My son is helping me disassemble things. He was 11 years old at the time. And there I'm holding the gasoline tank. Imagine this 80 pounds of gasoline, 10 gallons, around 40 liters of gasoline. Was right behind the seats of the car and separated from the driver and the passenger by about a 3mm thick piece of paperboard with some vinyl covering on it. And it had a flip top lid with just a little clasp to hold it down. So getting rid of that gasoline tank made me feel a lot more comfortable in the car. But of course, remember, this car had been sitting outside underneath the tarp for a long time, so it was in very bad shape. So the very next job after we got rid of the engine was we had to lift the body bucket off of the chassis or frame in order to be able to restore both the body and the frame. So once I had the body off, I hoisted the chassis up in the air and I beat on it with a dead blow mallet to knock all of the junk out of the frame, because there was lots of rust and sand, and also squirrels had been living in there, and they put nuts and leaves and other things in there, and I had to get all of that stuff out because it would hold water and cause the corrosion to be worse. And then I had lots and lots of rust holes to patch, and you can see I have lots of steel I had to weld in various places. And there my son is painting the chassis with epoxy. And then we had to put the body bucket back onto the frame, because the body bucket was in even worse shape than the frame. And by this point, of course, one of my problems is that I'm kind of a cheapskate. I don't like to spend money unless I have to, and sometimes I'm foolish that way, and I spend effort instead of money. And so, whereas you can buy some of these body panels still for these cars, I had to do the hard thing of bending little sheets of steel and welding them together in order to do these body repairs. I made my own floor pans for the car to replace them because they were completely gone. And you can see lower portions of the car were in very bad shape. They'd corroded away. In fact, this was a repair that someone else had made, and they didn't understand chemistry very well, because they used bronze to braze in the repair, and then the bronze and the steel set up a galvanic corrosion cell and corroded away the steel over the subsequent years. So when I did it, I welded it with steel, so there wasn't any galvanic problem anymore. Here's the motor with the motor to transmission mounting plate and the flywheel attached, and motor installed, as you can see there, with the transmission, and then a front battery box constructed. And my son is right now in this picture wiring up all of these batteries to be in series. And here I'm testing the layout of the rest of the components. This is the inverter. This is a box that has all of the wiring and relays and so on. And then this device was the charger, and it actually ended up here instead. Then there was a lot of work just to make it look pretty. But of course, I didn't do that until I'd actually tested the car to make sure that it worked. So first I took it out for a drive, and then I did all of this body work to make it look pretty. And this is the very first and also very last car that I will ever paint, because that job is just not a job that I could ever make money doing. It's too fussy and too slow and too painful. But I did paint it in my workshop. And here's the finished result, and it looks just a world of difference from the car that I had originally started with. It looked glorious, and I drove this car for about 16,000 miles. So what is that? About 25,000 kilometers back and forth to work, and I would plug it into a landscaping outlet, just a 1 kilowatt outlet, both at home and at work, and that's the only way I ever charged it, and it was just a delight. It was silent, the performance was exceptional, it looked very pretty. People were stopping me on the street and asking me about the car, or whenever it was parked. I took it to car shows. I loved this thing passionately, and for 4 years I drove it back and forth to work. The story is not done yet, but I just want to get into a few things that you hear about electric cars. Of course, there are a lot of people that would like the transition not to happen because they have an interest in maintaining gasoline cars as long into the future as possible. So some people will claim that making the battery consumes all of the benefit of using an electric car instead. And there's a kernel of truth in that. Batteries do have a high CO2 emissions intensity associated with making them, but if you recharge them on even a decent grid, it's paid back rather rapidly. And as batteries get cheaper, their emissions intensity also drops. Then there are lots of arguments. Oh, we'll run out of lithium. No, we'll never run out of lithium. We have so much lithium. We're drowning in lithium in brines all over the world. And in fact, some of my customers are working on lithium, selective lithium recovery projects for removing lithium from existing brines that are mined for other purposes, like making bromine. Then there's the worry about the grid. Well, of course, the grid has to green and it also has to expand, but it's not as bad as you think because of the efficiency as mentioned. It's also a bit of a myth that people are talking about how cars are going to become the storage for the grid, and that has difficulties associated with affording it because the batteries that are used in cars are not ideal for grid storage. They're too expensive for that purpose. So although I see some opportunity for that, especially in emergencies, I know that Ford is making this F-150 truck, and it has inverters mounted in it that are intended to use it as a job site generator for providing power for power tools and so on construction sites. The opportunity to use the car's batteries for these purposes is fairly obvious, but the economics still needs a bit of work. And I think a lot of these things people were very unfamiliar with electric cars back in 2014 when I did the project, and now those myths are kind of going away. But sadly, one day coming home from work, I was driving on Canada's busiest highway, Highway 401, through the central part of Toronto on my way home from work, and all of a sudden a big pickup truck with dual rear wheels changed lanes without looking, and he changed lanes into me and he smashed the car. In fact, he hit one side and spun the car around and then hit the other side and shoved the car down the road with me in it. And I'm very lucky to be alive, much less uninjured, and I was uninjured. The only thing that happened to me in this whole thing, there was no fire, there was no injury to me, but the only thing that happened was my cell phone screen got smashed as my leg hit the door window regulator. So I was very fortunate, but of course the car was destroyed, and you can imagine how much it hurt me and my son also, to see all of that effort, hundreds of hours doing careful body work and all that stuff. But of course, you know, life sometimes throws you this kind of a problem, and you just have to cope with it. Of course, cutting the car up into little pieces so that the scrap dealers who rove around in the neighborhood would come and pick it up, that was one of the most hurtful things that I did. And if you're attentive, you'll notice in the background, you can see that there's a piece of the hood of the car up in my office here. But as things would have it, by luck, none of the electric stuff in the car was damaged at all. It was in perfect condition after the crash. And then on top of it, I managed to get a settlement from the insurance company that allowed me to keep the car. And so all of that electric stuff just sat in my garage. And then I bought another British car. Being kind of foolish and in love with British cars, I bought another one. And this is a 1973 Triumph TR6. And it had a great big 2.5 liter straight 6-cylinder engine in it, which of course promptly killed itself. And I wasn't interested in fixing that. So I decided I was going to convert it. So guess what? We did the whole thing again, only this time with a TR6. So here comes out the engine with the transmission attached, and this engine weighed a lot. This was a giant cast iron behemoth. The great thing was that the cars were actually very similar, despite the TR6 being much larger and more powerful in terms of having an engine. So in fact, I only had to make this little plate here to adapt the drive shaft to the differential of the TR6. And that allowed me to basically drop things in just like in the other car. And in fact, even this cross member that was underneath the engine was in pretty much the same position as the one in the Spitfire. So dropping it in was really simple. And so here I am with the drivetrain. There's a guy on LinkedIn, an engine advocate, who liked to post pictures of people hugging their engine. So I hugged my electric drivetrain and sent the picture to him just to make him angry. But otherwise, we did very similar things. This time, battery box in the front, just like before, but I wanted the engine, or sorry, the motor to be more visible. And then you can see the pictures of all of the wiring work that had to go on, and the front battery pack being wired together. And then here in the bottom right, this is a yoga pose that's called upward facing electrician, that every British car owner knows at some point in his life, and I've known it several times now because of course I had to rewire the whole car. The dashboard had been destroyed, so I veneered it with some very pretty mahogany and put all the gauges in place, and rear battery pack just dropped right in just like the old one. This car was in much better shape, so there was no bodywork really needed, a little bit of fixing here and there. And here's the finished product. And this one, basically there's no, you look at it and it looks very much like an ordinary TR6, but it's silent. It doesn't have that roaring engine. And there's a picture of the engine compartment, which of course startles everyone when you open it and they look at it, because they've never seen anything like it. So if you're interested in these topics that I've been talking about, if you want to read more about the car project itself, either of them, or you want to read more about energy or about hydrogen, I refer you to my LinkedIn profile. You can go there, and all of these articles are available for free. They're written not like technical papers, but also not like a science popularist would write. Somewhere in the middle, where I make the things are technically accurate, but they're written in a way that's more accessible to the average person to read. And I update them as I learn and as new things come to my attention. And as I said, this is a project of great passion for me, and I hope that you found my discussion about it interesting, and I hope we'll have an engaging discussion in questions and answers. And that's my talk.
Yeah, thank you, sir. It was really wonderful to look at all this, and the step by step you have taken the things forward.
Right now, I apologize. I'm trying to display so I can see everyone's face again, because I turned that off while I was talking. But yes, by all means, if there are any questions, please feel free to forward them.
Yes, sir. I'll call the panel members to just put up their queries one by one.
Well, I have a question. I've gone through the presentation. It was really nice and wonderful. Particularly the motivation behind your electric car. It was really wonderful. I have a small query. Actually, it came to my mind while working on electric car here at the campus. It came to me that what are you going to do with the battery waste in the coming years?
Yes, it's a very good question. Go ahead.
So I'm really, I do not know what's the answer to this, but I'd like to hear from you, sir.
Sure. Well, being a chemical engineer and working in the capacity that I do, which is developing new or helping people develop new process technology, I do know a fair bit about this, and one of the good things that that one can that one can conclude as a chemist or as a chemical engineer looking at batteries is that the batteries themselves are really an excellent ore. So if we think about the ores that nature gives us, usually metals that are similar to one another in chemical properties, they're found together. And the beauty of a lithium-ion battery as a waste is that all of the hard work of separating the metals that are similar to one another chemically, that need to be separated from one another, has been done for you in the making of the material in the first place. So I'm not worried about battery recycling. Battery recycling right now, as far as the life cycle analyses of looking at whether or not it's a good idea to make electric cars and how much energy it takes to make batteries, they're ignoring recycling because they're saying, well, we don't have data for that yet, so let's be conservative and assume that there's no recycling. Well, of course, when recycling happens, the energy intensity per kilogram of all of those metals, you know, the battery contains aluminum and copper, and they're as metals, so recovering them is dead easy. It's just a matter of physically separating them and then melting them. It's so simple. But then there are the metals in the cathode. So the metals in the cathode are lithium, of course, but not very much, only about 130 grams per kilowatt hour of lithium metal. Depending on the battery chemistry, the other metals can either be nickel and cobalt and manganese, or they can be nickel and cobalt and aluminum, or iron phosphate, as in my battery's case. And recovering those metals, especially the nickel cobalt, which is worth the most money, separating nickel from cobalt is hard, but it's not required because they're so similar. And the great thing is there's no iron there. So as long as you keep the iron-containing batteries separate from the nickel cobalt batteries, the battery recycling is going to be really quite straightforward. And I think they'll be competing with one another to buy your battery, as opposed to having to pay them to process it as waste. I hope that answers the question to your satisfaction.
Yes, yes. I got my answer. Thank you for your valuable inputs.
No problem. By the way, it's happening already in China. And in fact, in North America and Europe, there are more companies developing battery recycling technology than can possibly survive at scale. So there's going to be a big consolidation as the people with the best technology and maybe the best financing and the best access to the dead batteries will become the market owners, and they'll build very big plants, and that's when it will become very economic.
Right, absolutely. Thank you.
Okay, sir, my question is, what are the drawbacks of outsourcing Chinese lithium-ion battery and using it commercially? And will they provide long-term service to our customers?
So, okay, so I understand that, you know, personally, I don't want to get into politics too much, but I think where everyone is right to be a little bit concerned about the dominance of China in the world. Of course, living in India, you're right next, you know, not far away, and already there are concerns there about the two giant emerging economies being in conflict with one another. So yeah, there are concerns about China having dominance in this area, but China has dominance in manufacturing of all sorts, and it's not a natural dominance. Let's just say that. By that, I mean that their dominance exists just because they were the low labor cost place in the world where the work was being done for the mobile electronics, for instance. It's not that China has any special advantage in terms of access to material or anything like that, really. One exception, I would say, we have to be a little bit careful about cobalt. Cobalt's problem as a metal is not that it's not abundant. Its problem is that it's abundant in the wrong country. And so this is a really significant problem. Of course, we engineers are not good at solving such problems. Perhaps it's not our job to solve them. But the trouble is that the Democratic Republic of Congo, where giant deposits of cobalt are found, is such a basket case of a country. I mean, it's dysfunctional, it's corrupt, and it's desperately poor. And so that's going to be some trouble. And the reason I say that China is tied up in this is that China will go where an ethical country or company or so on fears to tread. And so China is in the Congo in a big way. And there's lots of Chinese middlemen there buying the product of the mines that are done by, you know, children and poor people that are just digging rocks in order to make money for tomorrow's dinner. So there are geopolitical problems with batteries, but they, you know, in comparison to the geopolitical problems of fossil fuels, these things are really trivial. Did I answer your question, or did you? I think there were kind of two parts to it.
Yes, sir. Yes, sir. Sir, then what are the alternatives to lithium-ion batteries then?
Well, you know, the alternatives to lithium-ion batteries are for transport are other lithium-ion batteries. They're really, I have a very few things that I kind of believe in firmly, you know, kind of axioms, if you will. But one of them is that there's a test for whether or not a battery technology really exists. Because I don't know if you're watching the internet like I am, every day, it seems every day, you're hearing of a new breakthrough, you know, revolutionary breakthrough in battery technology. They're going to do this or that, you know, whatever it is. The big one at the moment seems to be solid state batteries. And I give people a very simple test. I say, here it is. If you have a battery technology and it's working in this cell phone, someone's cell phone, for 3 months, then it might be in cars 3 years later. And if it hasn't been in a cell phone for 3 months yet, really don't count on it really existing. It might be in the laboratory, it might be fun research, maybe it one day will turn into something, but it doesn't exist yet. It's not a market factor. Now for grid storage, I think there are other options to lithium-ion batteries that have much promise. But I don't see the next thing that replaces lithium or lithium ion in transport applications. I don't think such a thing exists yet. I'm not precluding that it could happen in the future. I mean, a miraculous thing would be someone comes up with a reversible zinc air or aluminum air battery that has a high cycle life and is reversible, but I think that really would be a miracle. It's very hard to imagine how technically it would be achieved. It would really be kind of a miracle. So I don't see any alternative to lithium ion in the near future, but I don't think there needs to be. I think lithium ion is already good enough. The thing that it needs to be is cheaper. And as it gets cheaper, its emissions intensity will drop. That's a fact. It's very difficult for something to get cheaper while it consumes more and more energy.
Okay, sir. Thank you.
Yeah, let me just expand it. For grid storage, you see, lithium-ion batteries are optimized around energy density per unit mass and volume. You know, they care about both of those things greatly. Grid storage doesn't care about those things at all. And so the optimal battery storage technology for grid storage will not be lithium-ion. Right now, lithium-ion it has a lot of advantages. It's cheap relative to what it used to be. It offers very, very high power, both on charging and discharging, and it's quite available and it's very efficient. Okay, and it has high energy density per unit mass and volume, so it's really quite nice. But the trouble is it's way too expensive for bulk grid storage, especially beyond a period of a day. No one would think to use lithium ion. It's just unimaginable. So there have to be other things for those longer term storage, and I think there are, but they're based on other metals like zinc or iron, maybe magnesium. There are a number of competitors, and no one is really clear which one will be which. I mean, vanadium is another one, but I don't think vanadium is scalable because I just don't think that mining vanadium is easily enough done to merit its use. It has the benefit of 5 electrons, which is really wonderful, but it's very expensive. So it's kind of hard to imagine that one is going to win.
Okay, okay. Is there anyone else in panels? Yeah, Professor Ankit, I hope you have posted one question there.
Yes, sir. Yes, sir. Sir, actually, I want to ask: is there any possibility to decrease the charging time? Because it usually takes 4 to 8 hours. So.
Oh no, that's in my car. Okay, so if I was to go out today and buy a Tesla Model 3, and I'm thinking about it because my Priuses are getting a little bit old, and eventually one day I'm going to have to replace them. I'm definitely buying an electric car. And you can take a Tesla to a Tesla charging station, and you can charge it to 80% of capacity in about 20 minutes. So does it need to be that fast? Does it need to be 5 minutes instead of 20? I'm not sure that that's a need. It's definitely a want. It's something that's quite convenient, but I don't think it's a need, because of course, if you want to charge in 5 minutes instead of 20, you need 5 times the power. And already the Tesla, in order to do the 20 minutes charge, it's charging at 125 to 150 kilowatts. That's a lot of power transfer, and that ultimately it takes a lot of big diameter of copper to carry that power. So the thing that's limiting the rate of charging actually isn't the power transfer on the front end, it's in the battery, and that's what this solid state battery business is really all about. If they do solid state batteries, and it's a big if, okay, but if they do solid state batteries really well, then the power transfer on charging can be improved a lot. And the reason for that is that the thing that's killing lithium-ion batteries over time mostly is the amount of time that they spend at high voltage. So generally they're at the highest voltage while they're being charged, also while they're hot. Because what happens is there are reactions that happen inside the battery between the lithium and the battery's components, like the electrolyte, that happen at high voltages, especially when it's hot, and they produce kind of garbage inside the battery that blocks off particles, so they're no longer available to participate in charging and discharging, and so you lose capacity. The solid state eliminates that because it gets rid of that electrolyte. The electrolyte in a solid state battery is generally a ceramic, a conductive ceramic, ion conductive ceramic. And as a consequence, that's the big benefit there. And it also gets rid of the fire risk. Because of course, if you look at these batteries, the trouble with them is that they have what's called an autothermal onset temperature. So at a certain temperature, which varies depending on the chemistry. So it's very high temperature for my lithium iron phosphate batteries, but it's quite a low temperature for the nickel, cobalt, aluminum cathode batteries that Tesla is using. There's a certain temperature at which, when you heat the battery up to that temperature, all of a sudden the reactions inside the battery between anode and cathode start happening, and they generate enough heat to make the reactions go faster, which makes more heat, which makes the reactions go faster, and it becomes autothermal. And once that happens, it's very difficult to stop a fire. A fire will start, and it's very difficult to put it out. And so the nice thing about solid state is that it gets rid of that flammable electrolyte, that combustible ethylene carbonate solution that's in there goes away. So that's the hope for faster charging. But again, I think 20 minutes is already pretty fast. I don't know. I don't need it to be faster than that myself. And like I said, I drove 16,000 miles with a car that took 4 to 8 hours to charge. And it was no trouble for me because what did I do? I drove it to work. The distance to work was the same every day. It was 37 miles, 61 kilometers. And I would plug it into plug at work, and I put in my day. And at the end of the day, long before the end of the day, the car was completely recharged, and I drove home. And when I got home in the evening, when the power prices got cheap, I plugged it back into the landscaping outlet. And in fact, that's how most charging is done by ordinary people that have electric cars. The challenge is, of course, they need a place to plug in. So I'm lucky. I have a house with a driveway and I can plug in. But there are a lot of people in the world who don't. So charging infrastructure becomes easier if the charge times are shorter, of course. But again, we need to not destroy the climate. We all need that, right? We only want to charge fast. We have to separate needs and wants. It's very important.
Okay, there are a few more questions in the panel, sir. Girish, you can unmute yourself and you can ask the question.
Yes, sir. My query was, as you mentioned earlier, that in EVs, as soon as we hit the power, the acceleration right kicks suddenly, which makes it a very rough start. So how can this effect can be minimized?
Okay, it can be, okay, but the beauty of these inverters is that they're computers and they're programmable. So it doesn't make it a rough start unless you want it to be a rough start, okay? And as someone driving a car for performance purposes, and I'm not a race car driver by any stretch of the imagination, But someone who wants to go very fast from a start, they have the option to do it. But if you want to go slow from a start, it's easy. With my car, you simply put it in 4th gear. And the beauty is that whereas if you tried to start your engine car in 4th gear, regardless how gently you let go of the clutch, you're going to have the tendency to stall the engine because the engine can't generate more than a certain critical amount of torque, especially at low RPM. And so it can't handle starting in 4th gear generally. But the electric car, there's nothing to stall. The inverter determines how much current goes into the motor windings, and that's determined by programming and also by how hard you're pushing on the accelerator. And in my car, the accelerator position is measured by a Hall effect device that mimics a potentiometer. So that thing, and that's connected to the accelerator pedal just like you would have on a modern drive-by-wire car. So yeah, you don't find it, certainly I don't find it to be a car that's unpleasant to drive with a jerky motion or anything like that. In the old days, of course, or with golf carts or things like that, where they didn't actually have inverters, they just had a bunch of kind of contactors that brought on various batteries or changed the arrangement from series to parallel or sorry, from parallel to series or the like in order to moderate the power output. You got very strange control behavior and a very unpleasant ride. But those days are long gone. I mean, the inverters are completely programmable, and you can tell it, with mine, you can limit the maximum torque. You can limit the rate of attack, how quickly it builds current, and everything is programmable. It's so wonderful.
Thank you.
Okay, we have another question from Pragya Sarkar. Pragya, you may unmute and you may.
So my question was, can you give us some of the differences between powertrain and drivetrain?
Okay, so I guess the answer depends on whose car. So in my car, all I did was just take the engine, throw it away, and bolt an electric motor to the same transmission that was in the car beforehand. And that's definitely possible, but that's not what an OEM would do if they started with a brand new design, because the beauty is that these modern permanent magnet AC motors that people like Nissan and Ford and Tesla are using, those motors are capable of spinning at very high RPM. I mean, 15,000 RPM. Whereas the motor that's in my little car project only is capable of going 6,000 RPM. So because of the limited top speed, I need a transmission. But for those modern electric cars that are made by OEMs, they don't bother with the transmission. They have a differential, and sometimes they have two motors and two differentials to give four-wheel drive, but they don't need variable gear ratios. They don't bother with them because the motor has so much torque that it can give very wonderful performance, acceleration, starting out at low speeds. And because the motor can spin very fast, it can achieve very high speeds when the motor is spinning at its top RPM. So the need for gear ratios basically is not there. But the differential is needed because otherwise you would need four motors, one for each wheel. And some people, I think, maybe who don't understand cars and their design very well, I don't claim to be an expert myself, but I do understand this. In an electric bicycle or motorcycle, often what's used is a hub motor. So they put generally a brushless DC motor in the hub of the wheel. And on a bicycle, this is fine, or a small motorcycle, moped type vehicle, this is fine. But in a car, it generates too much unsprung weight. And then you also have the problem, if you have four hub motors in a car, you need four inverters. The motors are in the worst possible place from an environment perspective. They get exposed to dirt and water and corrosion and other problems. And then there's a big failure mode problem. So what happens if one wheel motor suddenly ceases to work? or gets a crazy signal and over accelerates. So there are all kinds of failure modes that arise from trying to use one motor in each wheel that are really unpleasant, and the differential gets rid of most of those problems. So even Tesla, they're not putting 4 motors, they're using only 2, one to drive the 2 front wheels through a differential and one to drive the 2 rear wheels through a differential. So that's the difference between the 2 drivetrains. And the great thing is that, of course, the moving parts, number of moving parts and wear parts and maintenance parts in an electric vehicle, it's considerably lower than that of a gasoline or diesel engine vehicle. And ultimately, that's going to make the car cheaper if the batteries can be made cheaply enough, and they're already getting there. So the day is coming when the cheapest car you can buy is electric.
Thank you, sir.
So, Dr. Bano, you have also posted a question. Please, please unmute yourself and ask, sir.
Yes. Nice presentation, sir. In my point, as we know, the pure electric vehicle battery plays an important role. But how can we increase the battery life? Because the disposal and recycling of electric vehicle battery a serious challenge for the electric vehicle manufacturers. And how we can increase the battery lives?
So I've written an article where I evaluate realistically the battery life, and I think the battery life problem, it really is a problem only when you want to have batteries be very small. So for instance, in kind of plug-in hybrid arrangements where you have an engine that's there kind of as a safety blanket, you know, for the comfort of people in case they have to drive on a long trip. But most of the time the car is driven short distances on quite a small battery. That arrangement is where battery life might be troublesome. But honestly, the data that I'm seeing, and I'm not just trusting the OEM's data, I'm trusting the data collected by the owners of these cars that are publishing them. The data for battery degradation is really quite encouraging. Like, the batteries are already lasting long enough, in my opinion. And as a consequence, as long as we can recycle them at end of life, and I think they will be mostly recycled, they mostly will not be put in so-called second life applications for a variety of reasons that we probably don't have time to talk about right now. But as long as we recycle them at the end of life, I think we're going to end up with a system that will make the impacts of using personal enclosed transport in the form of electric cars dramatically less than that of what it's replacing, the gasoline or diesel engine car. So I think we're already pretty much there. And of course, every day they are going to get better and better. And remember that mechanism I mentioned where the high voltages cause degradation to the electrolyte? Well, of course, if solid state batteries one day, that problem of making solid state batteries and making them cheaply enough is solved, that will also solve the degradation problem quite a lot. Now, there are other mechanisms that can kick in and they may dominate. So who knows, maybe the cycle life won't improve, but by getting rid of the electrolyte, that would be a huge help. Getting rid of that liquid electrolyte would be a huge help to the improvement of the cycle life. Okay, are there any further questions?
Yeah, one more student has put a question. Vishal, you please go ahead. Vishal, somehow your voice is not audible actually. I'll read out the question, sir, which he has posted there. Okay. Sir, on what basis battery management systems are designed and what are the factors which are affecting the performance of battery?
Good question. So I didn't mention that, and it's kind of funny that I didn't mention it because it's really something I think is very important. So with lithium-ion batteries, especially the high energy density versions, the ones that are used in the OEM cars, like Tesla and so on. So those batteries, they absolutely require a battery management system. And so what I mean by that, it's two pieces. One piece is very simple. It's battery condition monitoring. So on every cell, and every group of cells in parallel is really one big cell. On every group of cells, you need to monitor voltage. And on chunks of the battery, that might be cell by cell, and sometimes it's groups of cells together, you also should monitor temperature. And the other thing that a battery management system does, aside from alarming and taking action based on battery individual cell voltages, is that sometimes, most often, a small amount of current is bypassed around batteries when they're at high voltage during charging. They call that balancing. And the idea is that we top balance batteries. So we want them to all be, if you think of it like each battery in a series battery pack is kind of like a tiny gasoline tank. And we want all of those gasoline tanks to be full at the same time. We don't want one to be full prematurely, because if you keep pouring into that header that's feeding every battery, and one of them gets full, it's going to overflow. It's going to get over full. And when it gets over full, the voltage rises very fast, and that's very dangerous because it can lead to lithium metal plating inside the battery. So the battery management system eliminates that possibility by monitoring the voltage on every cell. And if any cell goes high in voltage, it shuts off the charger completely. But if the battery voltage is just getting a little bit too high and this one is a little bit too full, then it can short some current to bypass that battery so that the others get a chance to fill up while this one stays at a constant level. And that function is called balancing. But the other thing that's needed, it's not needed for the lithium iron phosphate batteries like the ones that I have, because they're really safe. But the thing that you trade off there is that they have low energy density relative to what Tesla's doing. But with the Tesla type batteries, and especially if you want to charge them at very high currents and you want super performance out of your car, like 0 to 60 miles per hour in 2 seconds, you need to cool the batteries with a refrigerant cooling system. So it's not enough to simply cool them to the atmosphere. You need to actually do air conditioning, or a heat pump, in order to take heat out of the batteries and pump it into the environment. And that's part of a battery management. It's part of battery thermal management. And for those high energy density batteries, it's the only way that you get away with charging them this quickly. So that's the function. But on my car, it's very simple. I have a little circuit board that sits on top of each cell. And that circuit board has a relay, and it opens the contact of that tiny little relay whenever the voltage is above a certain set point or below a certain set point. And all of those relays are connected in series. So if any one cell is in alarm, it opens its relay, and then the whole circuit is open, and my inverter goes, oh, it's an alarm, and it will take action. In my case, actually, I have 2 separate actions. One of them operates the charger, shuts the charger off, and the other one gives an alarm in the driver's compartment, because I don't want it to automatically disconnect the batteries while I'm driving, because it could be a false alarm. So it just gives me an alarm, and I go, oh, I wonder if there's a problem. And of course, I have displays with voltages, and I can go and find out if the problem is real or imaginary before I take any action.
So we do still have a lot of questions, but I remember that you need to go for another webinar within next 10 minutes.
I do. I need to run in about 10 minutes. I would encourage your students and other attendees, if you're interested, please find my LinkedIn profile and go there and have a look, and send me a private message. I don't mind. If I'm busy, I may not respond, but I don't mind. Send me a private message, and feel free to ask questions after you've read my articles, and a lot of the questions will be answered in those articles. And otherwise, I thank you for your attention, and I hope it was useful and interesting for you. And I'm fascinated. I'll be very fascinated to see the results of the project, the car conversion that was done at your university. And it would be wonderful to come and visit sometime when we're allowed to travel again.
Yeah, it was a big pleasure hearing you, sir, today.
It's a pleasure to speak to you all, and I hope that you have a good rest of your evening.
Yeah, sir. Thank you.
Okay.
I'll just take a minute. Dean sir, I'd like you to just conclude this one. Somehow I think so. Might be some network issues. Anyway, sir, it was wonderful to see you touching all these new areas in the field of electrical vehicles, and I'm sure that the students and professors and many external attendees had a good learning today. Although we could not cover up all the questions, but I hope like we can have uh, the similar kind of sessions sometime again in future, and I'll keep the other questions posted to you. So thanks a lot, Mr. Martin, once again, and on behalf of the entire group, I hope to see you again in future addressing the IEM UEM family. And thanks to all attendees for joining us, and wish you a great day ahead.
Thank you very much.
Thank you, sir.
Bye-bye.
Thank you.